Good evening, everyone. Welcome back to this fourth day of the session on NEP Orientation and Sensitization Program. It is my pleasure to introduce our speaker for today's session on research and development, Professor Narayan Rangaraj, an esteemed scholar in industrial engineering and operation research, whose academic work and mentorship have significantly contributed to education and research. Professor Rangaraj has been a faculty member at IIT Bombay since 1990, bringing a wealth of knowledge and a deep commitment to advancing research. With a BTech in Mechanical Engineering from IIT Bombay and a PhD in Mathematical Sciences from Johns Hopkins University, his academic journey reflects a strong foundation in interdisciplinary thinking. His research focuses on operations research and its applications in areas such as public transport, railway operations, logistics, supply chain, and healthcare. His work has been widely published, showcasing both depth and breadth in addressing complex real life challenges. Professor Rangaraj has mentored numerous students, guiding theses and projects that contribute to the broader research ecosystem. As part of his academic endeavors, he has held visiting appointments at globally renowned institutions including IIT Guwahati, the National University of Singapore, Railway Staff College Vadodara, and the Fraunhofer Institute of Industrial and Applied Mathematics in Germany. He is also a fellow of the Operational Research Society of India. Today, as we discuss research and development, we look forward to hearing his perspective on fostering innovation, bridging disciplines, and addressing societal needs through academic and applied research. With that, I will request Professor Rangaraj to start his presentation.
So, good evening, everybody, and thanks for the invitation to speak on this topic, which is quite broad and I hope of relevance to all of us in the profession and in the field. So, I'll get started straight away. So, the topic assigned to me as part of this overall program is research and development. So, next slide. Uh, so our role as academics, I think it's I mean most of the audience here is academics, but actually I find that many people even now, even outside academics, have to take on this role at some point, because even industry people have to do training and manpower development and so on, and transmit existing knowledge. So teaching is done by more than academics these days. But anyway, our role as academics is teaching, which is provide a good learning environment for our students in terms of existing knowledge and building a worldview which is healthy and useful, and taking things forward. In research, it's a little fuzzier. It is to generate new knowledge of some kind. Either it is true and has some long-standing relevance as part of our search for truth, or it is at least elegant and aesthetically appealing in knowledge. For example, even existing knowledge, but presented in different forms, or useful in some way. I mean, there's some pragmatic element to it. It improves the human condition in some way or other. I mean, it increases our understanding in some tangible way that is useful to us. So, any of these or some combination of these would qualify as research, as long as the new knowledge is validated and verified in some way. And of course, we increasingly academics also have to do some administrative things. Many people in Maharashtra would be doing election duty tomorrow and those kind of things. That's fine. But in all these things, there are quite a few changes. Like organizations other than schools, colleges, and universities are doing all of these activities. I mean, teaching and research part. And today, it is true that students learn in a lot of different new and different ways from what most of us, for example, learned when we were students. So that is, I think, quite clear. Let's go ahead. So uh, I won't spend too much time on this. I'll straight away go to some examples of my own sort of journey in this area. But just some thoughts. We in academics, we think of knowledge being generated through a scientific process, through inquiry and through our own thoughts and experiments and other activities, observations, and then abstraction and various things, and then somehow it is applied to some real situation. This sometimes happens that new knowledge comes up in universities or some other institutions, and then it is applied in the real world in some useful way subsequently. But it is important to recognize that quite often it happens the other way. That means, when I say other way, I mean the driving force for the work does not come about purely from knowledge generation and thinking about things and building ideas and things like that, which are then transferred to the field. It is quite often, the case that laypersons or people in the field who are quite experienced, quite adept at various things, they do things, and then the scientific community or universities or students, they sort of start looking at it and realize that there is something interesting going on here, and then build a theory around it, which often then feeds into the field in quite useful ways. And there are many examples of these things also. So at least in the field that I work in, which is operations research and to some extent industrial engineering, uh, it is revolving around human activity, techno-economic systems. Actually, it started off by the term operations research has got some wartime history in the Second World War, when operations needed to be organized and planned in some way. But it has far outgrown that original term of operations research. But any organized human activity of a large scale, which is analyzed in a rigorous manner, and then the decision making in that is modeled and sort of often quantified and made rigorous. That is what operations research is all about. And so it could be applied to manufacturing, retailing, finance, healthcare, anything actually which human beings attempt to do in a systematic way. Dr. Prakash mentioned supply chains, logistics, any of these areas where humans sort of organize things and get things going. That qualifies for operations research, because there is a techno-economic system where resources are used and then some deliverables are generated, and those have to be done well and systematically, and serving the purpose, that is not wasteful, and also meeting the requirements of the beneficiaries of that system. So, for example, retailing, then the customers who are using that system, or if it is healthcare, then patients, and even doctors, and even healthcare providers, their needs also have to be met by the system that is being designed. Or you take an airport, operations in an airport have to be designed to meet the needs of various stakeholders in that system, including the airlines and the passengers and the service providers and the administration and the regulators and everybody using that system. So it's a fairly broad and general term, which has come to stay now for some strange reasons. That term operations research, or OR, or in Britain it is called operational research even now, and in the US and other places it is called operations research. In our department in IIT Bombay, we call it operations research. Also, sister discipline is industrial engineering, which is how industrial systems are organized. So, anyway, my own view is that any work from first principles, starting from understanding of the basic system, and then building a picture of it, and contributing to its understanding, and how to organize it effectively, that qualifies as some developmental work. And often, if you do it from first principles and do it afresh for new situations which keep arising from time to time, often there are research elements in it, because it is very unlikely that somebody would have already developed a model for how Amazon works or how Uber works or something. These are new creations, and there might have been trading and some aggregation in the past as well. But the exact way in which technology is used, certainly digitalization and so many things, almost many new features, and how humans are responding to that will always be new and fresh. So there'll always be interesting things to do as we go forward. Okay, next. So, uh, the field, as I said, is to do with rigorous study of human techno-economic systems, especially to do with decision making in those things. And they use mathematical tools and information technology tools and computation and some modeling. So it comprises modeling, mathematical and algorithmic aspects, together with its implementation also, supported by digital technologies. And it goes without saying that artificial intelligence and machine learning and the modern buzzwords, they are part of this whole activity. They are all pervasive. So since it goes without saying, I won't even say it actually. So some pillars of operations research are optimization, applied probability, statistics, simulation, game theory. So some of you may recognize some very familiar terms in these, but they are applied in new and interesting ways. Even good old principles from applied mathematics, they are being rediscovered even as we speak. Yeah, next. So the rest of the session, I plan to talk about the role of operation research in two areas. Uh, they are quite different, and in that sense, they have nothing to do with each other. They are just two areas of application in which I have been working. One is public transport planning, uh, on which I hope to spend about 30-35 minutes, and and I'll tell you a little bit about what I will do in that. And that this one I have been doing for almost my entire career, which is now close to 35 years, 34 years. So that is to do with how public transport is organized and planned, and decisions in public transport. And the second one is a rather new one, which is to do with sports in the modern world. And when I say sports, I don't mean computer gaming or something, but just ordinary, good old sports like tennis and table tennis and badminton and all that. Not so much chess and those kind of sports, which are more strategic, but you know interactive and sort of physical sports, where there is often an element of chance in the way that it evolves and how it plays out. So all common sports, table tennis, tennis, badminton, volleyball, and even things like baseball and cricket and anything actually. And here I'll be there are a lot of issues in this also, but I will focus in this session only on one thing, that is how is the game designed, that is how are winners decided, especially tiebreakers. That is because, see, it's not very difficult to think of how is the game structure when one player is a dominant player, but how are tiebreakers designed, and how they are executed, and how that affects the outcome of a game and its implications, not just tiebreakers, but in general game design. Yeah, so this is what I plan to talk about in the rest of the session. So I'm going to start with public transport planning in the next slide. Yeah. So this is operations research in models in public transport. This is part one of my talk. So I would, I don't know what is the way that you normally do it here, but I would be okay with being interrupted, and I can take some questions or clarifications uh, even midway after I speak for a few minutes maybe. Uh, we need not wait till the end of the session. We can even have something in between also. Okay. So an interesting area of application, at least for me, is public transport. Now, this is something that is fortunately of some relevance. In fact, I would say quite a bit of relevance in India, because we have had a lot of infrastructural improvements, especially in our cities in the last many years. But it is very clear that we need investment in public transport. We are our automobile sales and individual car sales are increasing, but it is very clear that our population cannot be sustained only on people moving around in cars. We need to invest in other modes of this thing, mobility. Walking and bicycling are there, and even that needs to be designed well. But I would talk today about public transport, namely, what we normally understand: metro, buses, suburban rail, trams. Uh, so Delhi Metro, I think it's fair to say, at least for quite a good number of people, has transformed the mobility possibilities in the city. Buses have been very important, moving to for people to move around for various purposes, including employment, education, social, travel, leisure, everything. Uh, Many cities in the country and world, including Chennai and many others, Bombay also. Definitely in Mumbai, suburban rail is continues to be a lifeline of the city and transports huge numbers of people every single day. In fact, one of the iconic images, at least for residents of Mumbai like me, is even during the bomb blasts which happened, serial bomb blasts. The suburban rail started functioning just a few hours after that, and that was a sign that the city would sort of find its feet again and start functioning, and that was a big sort of morale booster for the population, if for those who recall that time. And in many cities in the world, including many parts of the Western world, and also other places, like especially cities like Berlin, Melbourne, and so on, trams are quite important even today. And in fact, those networks are expanding. Yeah. Calcutta tram, unfortunately, is almost dead, but I hope we find a way to revive it. But anyway, yeah. Next. So I will talk. I will not talk so much about mainline train operations. The long distance train, although that is a very significant segment of public transport in India. But I won't talk much about it. There are many interesting issues, and uh, our group at IIT Bombay, we have worked on that quite a quite a bit. But there are many significant aspects. They also carry a very large number of people over long distances, and uh, in many places it is a shared network. Now there are two dedicated freight corridors coming up in various stages of completion, and one from the north to the east and one from the north to the western coast. But by and large, the bulk of the Indian Railway network shares capacity of passenger operations with freight movement. Yeah, and next one. So I'm going to talk today about public transport, and as an example, suburban rail carries, actually I think closer to 7 million passengers every day. Delhi Metro carries a very large number of people. Even 2 3 years ago, it was already more than 2 million, and freight is still quite important. And you can see this is probably a picture from Delhi when you could see something, and you know uh, the metro is moving, and road transport is pretty much choked. Yeah, next. I won't talk much about freight, but freight is also very important. So, as I said, examples of viable public transport. The top right is Bombay Suburban Rail. Bottom left is the U-Bahn or the metro in Berlin, in Eberswalder Strasse, which is one of the iconic sort of junction points where many modes of transport. It's an old photograph, but still one which is very popularly shown for, I mean, it's a representative of the Berlin tram, I mean, Berlin subway system. And bottom right is the Berlin tram. I mean, nothing very particular about these except the ones on the right, both the top right and bottom right are pictures that I have taken. So just for that reason. Yeah, next. So I'm going to talk about next slide. So I'm going to talk about questions like uh, no, I think the previous one, I think. Yeah. So, for example, if you take just a standard bus route, then you can ask questions. I mean, assume that it is designed in some way. That itself is an interesting issue. That what is the right design of a bus route? That is, from where to where should it ply? Let us say that some route planning has gone into it. That is actually turns out to be quite a complicated question in itself. It's not just one route; it's a route network which is usually which requires to be designed. But let us say that somebody or other has decided that Route 469 goes from Ambedkar Nagar terminal to Anand Vihar terminal in Delhi. It is a 28-kilometer route, and it is a very frequent bus. Let us say that it is we want it to run at every 5 minutes. Then one of the questions is, how many buses do we need, and you know how to schedule them. I mean, it's fairly straightforward once I place the question on the table in this manner. We need to estimate the round trip time and give some time for turnaround, and then pump enough buses so that every 5 minutes there's a bus, and allow for some little bit of fluctuation in travel times because of traffic and so on, and then uh, see that the frequency is maintained. Then there are those who use buses. I don't know how many people in this audience use buses these days, but some of you may have used it as students or whatever. There are many problems of bunching of buses, and how to sort of have a smooth bus operation. But one can approach the problem fairly logically, and controllers of bus operations in all cities in India which run bus services do this kind of thing. Yeah. So next. Uh, then there are many other questions that, in the peak hour, we would like to run more services, but in the off peak, we would not need so many because they would be run unnecessarily, empty. So then how to ramp it up and ramp it down, and then how to have the crew to operate these services, and where do these buses go in the off peak time, and where should they start from, and how to do it so that the cost is kept as low as possible, but still the service is maintained. So all these issues regarding bus route planning, bus route frequency planning as well as uh, the crew allocation to these buses. These can be approached systematically, and we indeed have some tools for some of these type of questions. I use the example of bus, but the similar thing is there for metro, suburban rail, and so on. Yeah, next one. Uh, so, for example, this is the U3 metro line or U-Bahn in Berlin, and it has got a certain route, and it a similar thing. So it takes about 40 minutes to go from end to end. So you can ask a similar question, and that's an example from Berlin. Next one. Uh, uh, One of the bus routes in Berlin, it has got a frequency of 5 minutes in the daytime, which is from 6:30 to 8 p.m. actually. So actually full day, but in the early morning and late night, it has got a frequency of 10 minutes. And there's a different schedule in the on Saturdays and Sundays and so on. So there's a detailed plan of the frequency of any of these transport. So this is for bus. The previous one was for metro, and earlier one was for a typical bus route. Yeah, next one. Uh, this is a suburban rail timetable in Bombay. I mean, not the timetable, but a sort of abstracted version. So uh, this is a tabular form of a timetable. As you can see, it has timings. So if you go down a column, the very first column is certain stations, and then the next 4 or 5 columns, they are timings of various trains. So they have some arrival and departure times at certain stations, and in certain stations they have only the departure time, because there the arrival time and departure time are just about 15 seconds apart. But where they have a significant halt, let's say a minute or at least half a minute, then you arrival time and departure time. So some of you may be interested in knowing that at least Western Railway in Bombay does timetabling at the level of half a minute. Uh, and in fact, it's certain detailed internal documents, they even do it to one-fourth of a minute. Now, this may seem a bit absurd when we are talking about train delays of many hours and all in long distance. But believe me, in suburban operations, half a minute makes a difference, because when you have trains that running at a frequency of every 3 minutes, you can imagine that the load builds up in 3 minutes, and trains are quite crowded, as you must have seen photographs or experienced it yourself. So so half a minute difference in planning, it does make a difference. And even in long distance operations, actually, if you round off all half minutes to 1 minute and then do timetabling at that level, you will find that the Bombay Delhi Rajdhani will take 50 minutes more than what it should take. And in fact, I would say that uh, you can easily improve the running of several long distance trains if you do more accurate timetabling. So this is an example of a timetable. As you can see, the column represents the vertical uh, timings of one train, and there is obviously a relationship between those numbers, the traversal time between one station to another station, and also the halt times wherever it has an arrival and departure time. Now, if you go across a row, it tells you all the trains at a given station, and it tells you something about the frequency of trains at that station, and also the headway, that is the time difference between two trains. Uh, and You can very well imagine that for safety reasons, the headway cannot be too small, because trains have to have a safe distance between them. The frequency cannot be too large, in the sense that the time difference between two trains on a given track or for a given destination should not be too much. I hope to have a train every 10 minutes or every 15 minutes or whatever is the desired thing. And here, supposing I have three trains an hour, and they turn out to be at 10:10, 10:20, and 10:30, and then there is no train for 40 minutes. That is not a good timetable. So when I say there are three trains an hour to some place, there's an implicit understanding that roughly every 20 minutes there would be a train. So when we say frequency, we are giving a certain time window and certain number of services operating in that time, but also that they are uniformly sort of spread, so that the service level is good. Uh, so these are all some of the mathematical constraints which are relevant to the timetabling problem. So traversal time, halt time, headway, which is the difference between two services on a same on the same line, let us say, and frequency, which is the uniform distribution of services in a given time frame. So all of these actually turn out to be linear uh, equality and inequality constraints between the timing variables. You can think of it that way. and that is quite useful when we want to mathematically approach the timetabling problem. So at this point, I'll just stop for half a minute just to verify that I am making some sense in what I'm talking about. If there are any questions, of course, I would be happy to answer. But also just that I'm getting through the flavor of the topic. One related question to a timetable. So timetabling is an operating plan by the service provider. Let us say the train company or a bus company. Now, uh, they plan it with a certain view of providing a certain frequency and a certain vehicle requirement, and then they have to plan their crew and also their maintenance activities and various other things, which you can easily imagine, even if you are not really thought about this issue from that point of view. But let us look at it from the customer point of view just for a minute. That what is the time waiting time for customers? So one interesting thing from queuing theory or from applied probability is that supposing buses are there every 5 minutes, then if we assume that people come to the bus stop at a uniform rate, I don't, and that is one of the features of public transport, in especially in the urban setting, that uh, at least in Bombay, at least for the bulk of the commuters in the main island part of the city, you may target a particular train, but the fun of public transport, which is frequent and well serviced, is that you expect a certain frequency, and you just go to the station and you show up, and within some minutes you expect to find a train to your destination, or a bus. So supposing I tell you that there is, on this route we spoke about, some bus route which is there every 5 minutes. Uh, so then I'm not going to time it exactly so that I go there at the right exact minute that the bus comes or something. I go to the bus stop, and then if I've just missed a bus, I wait for 5 minutes. If I go there and the bus immediately comes, then I wait for close to 0 minutes. On average, I wait for 2.5 minutes. I mean, that is the rough calculation. Uh, and this is true if buses are evenly spaced and they are operating as per the desired plan. But in the supposing there is bunching of buses, then in the extreme case, the average waiting time may be closer to 5 minutes, because if there are bunching of buses, let's say, because of traffic lights or because of congestion, etc., there's bunching of buses, and uh, there are two buses every 10 minutes, but they both arrive together, and then there's nothing for 10 minutes, and then again two buses come, then there are two buses every 10 minutes, but then the waiting time is effectively 5 minutes on average again. So the waiting time paradox, which some of you may be familiar with, those who have studied some queuing theory or applied probability or something, is that if inter-arrival times between, say, buses are exponentially distributed, that means that they are completely random, but with a certain mean. I mean, I can tell you the mean time is something, but other than that, it's a completely random time. It can take on pretty much any time, and sometimes very large times, and sometimes very short times between buses. Then it turns out that the average waiting time is close to the inter-arrival time between buses, which is a little bit paradoxical. But if you think about it, it's not really the case, in the sense that supposing there is bunching of buses, then if people come in a regular stream, then an average customer is much more likely to come in the longer interval than the shorter interval. So many more customers have to wait, for the longer period than those who come just in between those two bunched buses or something like that. So it turns out that in the case of exponentially distributed waiting inter-arrival times, the average waiting time for a customer is the same as the average inter-arrival time. So that is something to keep in mind when planning services and so on. Yeah, next one.
There is a question on chat which
Yes,
asks by Professor Maitai, is there
yes.
any mechanism to take care of uncertain traffic congestion?
Uh, so there are two ways of thinking about this. That as a service provider, like a bus operator, can I do anything about traffic congestion? Yes, I can ask for bus lanes or dedicated bus corridors or something. Beyond that, it may not really be in my control. Then I have to just react to the situation and then do what I can as a bus service provider. So there are two ways. One is, can I actively do something about the congestion, but that is a traffic planner's role for the city at large, not just a bus operator, but the entire all stakeholders. And in some cases, if the problem is really extreme, so for example, in cities like Ahmedabad, Surat, and some other cities, especially in South America and some other places where they have tried it successfully. They have bus corridors or the bus rapid transit system where dedicated capacity is made available for mass transit options. And in a sense, that is really the one of the big advantages of having a metro or suburban rail or dedicated tram lines and so on, that the transit time is controlled by providing dedicated capacity for these options. And there, that in a sense, the traffic that the uh, public transport vehicle is dealing with is controlled, and so therefore it is managed at that level. But the other one, where the bus is using the same resources as the rest of the population, including cars and pedestrians and cyclists and bullock carts and everything else, then one has to take a reactive stance and then just do the best we can, and then maybe monitor the situation and pump in some more buses if there's a big pile up somewhere, or pile up meaning bunching somewhere, and so that the situation is addressed to some extent. That I mean, there's not much you can do about the primary phenomenon itself. Yeah. uh, yeah, so the next one, please. So yeah, so this is what I just said. Actually, I just said this in words. So we'll go to the next slide. uh, so one specific aspect of public transport planning is periodic scheduling, which I mentioned in qualitative terms, that when if we are talking about, let us say, urban commuting, for regional services over longer distances, the considerations are slightly different. But even then, there is an element of this thing that people will not use a public transport alternative if they are very infrequent and just once a day in some arbitrary time. You cannot really have the flexibility of using that as a mode of really regular use. Then people would rather use their own vehicle. So one of the features that makes public transport attractive, and this has been shown in repeated studies worldwide, that unless you provide a reasonable frequency, because everybody cannot, target a very particular service and then take a particular service back. That is like a contract bus or a contracted service that is serving some of the people, but for a large number of users, they need options and they need some flexibility as to their time of travel, and there is a expectation of a good frequency of services. So even recently, we heard that even in Mumbai, the new line which has been opened up near JNPT, Jawaharlal Nehru Port in Uran, commuters are asking for more services on certain lines because the traffic is growing, and they feel that one service every half an hour is not cutting it. We would like at least every 20 minutes and so on. So there are obviously constraints on the number of rakes available and all those things. But unless people express their demands and say what they want, it does not happen. So periodic scheduling is one of the ways of planning such operations, where you attempt to get a certain frequency. And uh, Now, supposing we take the blue metro line in Delhi, which has got a Y-shaped geometry. On the western side, Dwarka side, it has got one branch, and on the eastern side, that is the Trans Yamuna side, it has got two branches. Then you have to really plan it. What do you want to do with this? So one way is to take one of those eastern branches on one of the sides and provide a linkage to the junction point. And then people have to change and then connect to the other service. That is one option. The other is to say that I'll provide a service from the left side to one of the branches on the right side, and then to the other branch on the right side. So I take one stem of the Y, and then the next service is to the other stem of the Y, which is quite commonly done. Supposing we want every alternate service to go to one of the branches and the other service to go to the remaining branch, then one can do it. It's quite easy. You may have to play around a little bit with the turnaround time, so that the two services, the return services from the two branches, they don't arrive at the junction point at the same time, because otherwise then one of them will have to wait for 3-4 minutes and things like that, which is an avoidable thing in public transport. So with a little bit of staggering of those two branches, the return trip, you can easily achieve these type of goals. But things can get a little more complicated. Supposing you want one of every three services to run in the upper branch and two of every three services to the lower branch, uh, and so on. There are variants of this problem. So supposing we take this kind of thing, now supposing I want one of three services to run on the upper branch and two of three services to run the lower branch. That is what the demand says, that there are more people using the lower branch on the right side. When I say the right side, I mean the right of the slide. So I hope it's clear what I mean. Yeah. Uh, So where it splits into two, uh, so the blank part, I mean the white part of the slide where the network splits into two. There, supposing the lower branch we want two of three services, and the upper branch we want one of three services. Let's say services start from the left side uh, e- every 5 minutes, and so in once every 10 minutes it goes up, and twice every 15 minutes it goes down. Sorry, once every 15 minutes it goes up, and twice every 15 minutes it goes down. So then there are different options as to how you do this. So the next slide. So yeah, this is maybe I should have used this right in the beginning. So there is this. Uh, so there is this Noida city center is the bottom right, and Vaishali is I think the top right, and Dwarka something or other is the left side end of the line. So if we want to timetable services on this network, then we have some options as to how to provide this thing. So maybe next. Yeah. So there is this concept of cyclic timetabling, which is that you provide a regular frequency every so often. So there is a concept of a cyclic timetable. So let us say that the term takt time is used in industrial engineering. Also, I believe Japanese and German systems to describe cycle times, which is related to what I said about headway and frequency. So headway is, as I said, it's a more a safety term, which is the time difference between two consecutive services. It can also be viewed as a safe distance between two services, but time is easier to imagine in the timetabling context. Frequency is the number of services in some time unit, and it is usually understood that when we say frequency, it is uniformly distributed in the time unit of interest. Okay, so if we go further, so if maybe I'll go through this somewhat quickly, but just to make the point that it's similar to the example that showed you in the blue line. Uh, so supposing we have it's also clear from experience and under our understanding of demand that all services need not run end to end. You can have services running on part of the network. In most metro systems, it is quite common. In many metro systems, it is quite common to have services going to end. But I think uh, everybody would have used a system where services don't run end to end always. There are some services which go all the way to the end or something. But so, for example, let's take a network going from A to B to C, and uh, B to C is the heavily traveled part of the network, so we want more frequent service there. And there are two reasons for this. One is the part from A to B then is more sparsely utilized, so we don't need so many services. And the other advantage is if we do a short turn of services from B to C, then our vehicle, which is doing providing these services, can get back quicker and is able to do more services. So actually, we are able to increase the service provision for customers, especially on the more heavily demanded section. So by doing these short-term services, we are able to actually improve the service capacity as well as improve the utilization of our vehicle. So both the things. So next slide. So for example, supposing I have uh, three services. So services uh, every I mean, in a 20-minute period, I have three services. Okay. If you see the arrival times at C in the left table, they are coming at 6:30, 6:36, 6:43, 6:50. So it's a sort of 6-minute gap, 7-minute gap, 6-minute gap, and so on. So this pattern keeps on repeating. A 6-minute gap, 7-minute gap, 7-minute gap, that makes 20 minutes, and then the pattern keeps on repeating. So every 20 minutes there are three services reaching C. But let us look at what happens at B. You have two options actually. If you want to make it uniform at B, then this is the pattern that they will leave B at appropriately time phase. So they will leave B at those times, so that at B you will see those same frequencies. But the result of that is that at A you will see, because remember that we want two services from B and one service from A. or sorry, the other way around. Two services from A and one service from B. So the first two services in this case are from A, and then the next service is from B to C, where there's an additional service every 20 minutes. So what you see is that the service pattern at A is there is a train after 15 or a bus after 6 minutes, then there's a 14-minute gap, then there's a 6-minute gap, 14-minute gap, and so on. So it's all right, but if you happen to come to A at if you just miss something, then you might have to wait up to 14 minutes. That may not be a good thing. Whereas if you look at the timetable suggested on the right, then it is uniform at A. Every 10 minutes there is a service, but at B you have a irregular pattern. You have a service after 10 minutes, 5 minutes, 5 minutes, 10 minutes, 5 minutes, 5 minutes. So at it's a trade-off between having a uniform service at A or a uniform service at B. And if you expand this idea to multiple routes and multiple networks, then you have to take a call. Where do you want the uniformity? So that the waiting time is more controlled and so on. It's also to do with the density of passengers coming in and so on. So you have all these various options for designing a timetable, even a very small timetable on small part of the network. You have different options in designing a periodic timetable. And the next slide. So this is formalized by this thing called a cyclic schedule, which is very compact to plan. You just say that you have services every so often, like every hour. This is the timetable, and it is repeated every so often. So cyclic schedules are described in a very compact way by telling what happens in a period, and then that period repeats. So I think I've got some examples in the subsequent slides. uh, yeah, next slide. So, for example, here is a commuter rail service in Los Angeles, Orange County. So you can see that there is a service every 2 hours from Oceanside to Los Angeles Union Station. Every 2 hours there's a train, 4:57, 6:57. So basically, at 57 minutes past the hour, every 2 hours there's a train. So it's a frequency of once in 2 hours. So obviously that translates to similar times at various other stations, with some minor differences, because you might have some special halts because of the name. But by and large, it is a once every 2 hour type of service. So this makes things very easy to for people to plan. That they know that if they miss a particular train, they have an option 2 hours from now, so they will plan it accordingly. This is not a very heavily traveled line, so it is once in 2 hours. So, but in Bombay, you have services every 3 minutes for the densest part of the network. But in the outlying stations, those spurs which go to the ends of the line, you may have a service every half an hour, every even every hour sometimes, for some of the stations. Yeah, next slide. So there are issues in public in planning of these cyclic timetables. So I will go a little faster just to illustrate the issue more graphically. I'll just maybe go to the next slide. Yeah, here. So just think of it as a geometry problem or a geometry decision. I have uh, two destinations which share the same line from one point onwards. Let us say, or even the short term business. So I have got services from A to D and also B to C. So B to C is the congested part of the network, and I want more services in that part. So I have in the middle part I have services uh, every 15 minutes. And A to D has got services every 20 minutes. So every 20 minutes means three times an hour, and every 15 minutes means 4 times an hour. So in the middle stem of the network, I have got a service every meaning 7 services an hour. Okay. So now how do I sort of make this uniform in some way? So I've got a red square and a red and a green triangle. So I have to and this pattern repeats every hour. Okay. So the leftmost circle says that the green services are at 0 minutes past the hour, 20 minutes past the hour, and 40 minutes past the hour, right? And the red square on the leftmost circle says that I have services at 20 minutes past the hour, 35 minutes past the hour, 50 minutes past the hour, and 5 minutes past the hour. So those are the four vertices of the red square. Now, if I rotate either the triangle or the square, I will get a similar periodicity. because it's just so many times. Four times an hour means four vertices of the rectangle of the square on the clock face of 1 hour. And triangle means three services an hour. And if the triangle is a rigid triangle and I rotate it, then I get services every 20 minutes. It doesn't matter whether I have services every 0 minutes, 20 minutes, 40 minutes, or 5 minutes, 25 minutes, 45 minutes. Yeah, ultimately, I'm getting a service of frequency 20 minutes. I hope that this concept is clear. So by rotating these triangles and squares, one can get different timetables. Now, supposing I have an additional constraint that at every station you need a gap of at least 5 minutes. Then the question is that I have to rotate them so that the vertices of both the triangles and the squares put together, they are 5 minutes apart. It turns out that you can't do this really. So although I'm running only 7 services an hour, so that is 35 minutes, 5 minutes apart, but I can't achieve the frequency as well as the headway in a uniform way. So if you go to the next one, but if I distort one of them a little bit, I make, instead of the square, I make it a quadrilateral with the minimum distortion. Then I can get something which is 5 minutes spaced, and then I can get some valid timetable where now all vertices are 5 minutes apart, or at least 5 minutes apart. So I can now play around with this sort of timetabling problem now as a pure geometry problem, and I can achieve different goals regarding frequency and periodic event scheduling. So this is formalized. The next slide says that this is formalized as the periodic event scheduling problem. And it turns out that this is quite a nice combinatorial sort of problem, and it has got an integer programming formulation and so on. And this has been sort of applied in some way. We have also tried it for various things, including Delhi Metro. With some, implementing all these things is a long journey, but we have had some success in conveying these ideas to them. Yeah. So next one. Yeah. So it turns out that if we write these constraints of headway and frequency and other things on in arithmetic, then it turns out to be modulo T arithmetic. That means if I have services at 5 minutes past the hour, 25 minutes past the hour, and 45 minutes past the hour, that is every 20 minutes. The arithmetic should show that 25 minus 5 is 20, 45 minus 25 is 20, but 45 minus 5 is not 20. So it is actually 5 minus 45 is minus 20, which I will interpret as 20. So I will, I have to define an arithmetic where, if I get negative numbers, then I have to add 60 to it and so on. So 5 minus 45 is actually minus 40. So that makes it, I have to add 60 to it to get 20. So I need an arithmetic which says that the time difference between 45 minutes past the hour and 5 minutes past the hour is the number 20. So I have to take 5 minus 45, and that makes it 20. But how do I get 20? 5 minus 45 is minus 40, and I have to add 62 to get 20. So modulo T arithmetic is what I need to use. So then it turns out that I can express all these constraints in a systematic and rigorous way, and sort of plan these timetables in a system, rigorous manner. Yeah. So next one. So it turns out that those who are familiar with linear programming, this is an extension of linear programming, but with integer variables representing these modulo variables. So I won't get into the details of that, but it is possible to represent it rigorously with a little bit of modeling effort. Yeah. Next. So we have tried some version of this in the Bombay suburban system to multiple destinations, and at least conveyed our ideas Central Railway and so on. So this is from VT station Chhatrapati Shivaji terminus to various destinations. As you can see, there is a pentagon here, which is the green one, and then there's a triangle here, which is the sort of purple one, and then there are some services which are twice an hour and so on. So they're all sort of roughly evenly spaced in the clock face of 1 hour, and there is a gap of at least 3 minutes between different services. Yeah. Next one. I'll skip this, but I've spoken a little bit about this double Y and double Y and so on, similar things. I think the next one has the double Y type of network in Berlin, where this type of thing has been actually done, of achieving certain frequencies in different parts of the network and then putting it all together to get a consistent timetable. Yeah. Next one. As I said, we applied this on the Bombay suburban network, and the blue part of the network on the bottom part of the thing, which is, starting the bottom part and then going up, the blue as well as the light blue. Yeah. So on that part of the network, we tried this with with some at least convincing way of doing it. Yeah. Please go ahead. This I've already spoken about, but this is the type of timetable which this thing. So metro network in Delhi, some people may be familiar with. Some of course, metro is a different thing because there are dedicated lines for each line, and there is no merging, and but you do have these Y-shaped lines and so on. So yeah, you can go ahead. There are many other interesting problems in public transport networks like route planning and then so on. You can go ahead. And the whole sort of conceptual model is what my colleague in Germany has proposed, like what she calls an eigen model or a characteristic model between line planning, which is the deciding which services to run, how many short term, how many to which end, and so on. The route planning, the timetabling, which is the detailed timetable of timings, and then the vehicle scheduling, which is the assigning of vehicles to this thing. So this she has given a sort of conceptual model for this, and most of these things they involve some fairly standard, but also some innovative mathematical models arising from optimization and other devices to come up with these type of solutions. Yeah, next one. So I think this is the last one regarding public transport. There are many interesting techniques one can bring to bear on public transport planning: dynamic programming, computer science, search procedures, periodic event scheduling, which I said is an integer program, a periodic timetable, which is a straightforward math programming problem, vehicle planning, which has got several heuristics and also linear programming, crew planning, which I have not talked about, but you can imagine it has got very interesting math programming formulations, and capacity planning, which probably requires simulation and scenario generation type of approaches. Yeah, next. Yeah. So I want to take a 1 minute break here and see if there are any questions or reactions before I talk about sports. Is there anybody who wishes to say anything regarding public transport planning and OR, or anything? It need not even be very directly related to what I tried to present, but even a general thing that what would be involved in this whole activity based on your own perception. That is also okay.
I mean, in
Please do.
general, I think everybody has used these services, so it's really fascinating to know in depth about how they do such scheduling. But I
Right.
mean, there are a
So
lot of
I
there must be a lot of algorithms, right? You have broken it down into concepts, but a
right.
lot of
So I
research must be going into
Yeah.
algorithms.
So here, the truth of the matter is what I spoke about in the beginning. That is, I would like to say that many of these things are algorithmically done the way I presented it. That is, conceptually, something is abstracted and then a logic is built and then that is made into an algorithm. That is what is implemented. It is not by and large. That is, people have been running bus services and other things long before linear programming was formalized, and so therefore there's a lot of practical sort of intelligence built into constructive ways of building operating plans, and in some cases I would say that they have been improved by these techniques. In a few cases they have been sort of revolutionized by these techniques, like for example the Dutch national railway timetable somewhere in the late 90s or early 2000s was sort of redone completely with these type of techniques that had some success, but by and large it is an experience driven activity like many human things, because the experience of planners is vast, and also they are able to take care of all the considerations in a very holistic manner by their experience, and sometimes it may be imperfect in terms of optimization or something, but the benefit is that it takes care of all the little details that have to be in place for it to be a realistic and feasible implementation. So, whereas if we give a technical solution based on an optimization model, that then has to be tailored to meet the real requirements, and many of them are some human requirements, flexibility, and some organizational needs of specific things for that particular line, and some details of a particular terminal or so on, which planners have internalized by their own experience over the years, and which they are very comfortable in doing. In a few cases, they have accepted sort of reworking based on technical solutions. So, for example, Delhi Metro, they are sort of thinking of doing something that we have jointly come up with. I would say that Indian Railways, which is a very big entity, uh, the 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 mainline timetable, which was done in 2021, just after the COVID period ended, and there was a reworking of several trains. That was at least done partly based on our joint efforts. I won't say we did the timetable or something, but there was a lot of joint work in developing the timetable for the mainline trains on the golden quadrilateral and diagonals. That means Bombay, Delhi, Calcutta, Chennai, the four sort of major metros, plus the diagonals connecting these things. So six major routes, which account for a very good chunk of passenger traffic as well as freight traffic. Actually, I would say almost 50% of Indian Railway movement. Uh, this was significantly redone with a fairly large joint effort in which we were also part of. So I can't say that these these algorithms have done it, but they have definitely supported such efforts to read, especially when things need to be redone. If it is an incremental change from last year's timetable, which has been fine tuned by years of experience, it is very difficult to do something for algorithmically, except some little bit of automation of some task like an Excel, or some basic spreadsheet type decision support. But when there is an opportunity to redo something and sort of do it afresh, then one can really think afresh and come up with new solution. That happens once in a while. That is my long answer to your sort of implied query, that there are algorithms and procedures, and many of them are increasingly used by planners as part of their subroutines. Mostly fairly standard things like what I said, traversal times, and you go down a column for a train. It is just a linear, you have to add so and so times to various things to get the next arrival time and so on. So these things have been automated partly using fairly simple spreadsheet tools. So they are also algorithms, but fairly straightforward. But putting it all together to come up with the entirety, that is not as common as maybe one would. I won't say one would like, but it is not that commonly seen worldwide. It's not just in India or something. But uh, there has been a significant impact in many parts of the world, including now in India. We continue to work very closely with both railways and some of the metro corporations. So there is increasing acceptance of these ways of doing things, and yeah, so they will have their own. It will have its own impact.
I assume there are metrics to keep track of the improvement as well, because
Yes,
uh,
yes. That also
study.
is something that has been systematically happening over the last few years. See, for example, now Delhi Metro being a corporation, separate sort of entity, it is very sort of sensitive to revenue, as well as passenger loads, as well as crowding and sort of occupancy, as well as costs associated with their whole operation, because it's a self-contained thing and they can monitor much more closely. So they have a lot of nice metrics which are world sort of standard, and they have also built up their own ways of doing it. Whereas you take Bombay Suburban, it is part of a very big system. It is a very small part of the Indian railway operation. Many resources are shared. It's not very easy to say whether the Bombay Suburban system is. Of course, there are some visible public measures like frequency and overcrowding of trains. But if you look at it as a service provider, how much is Bombay Suburban system spending and what are they getting out of it? That is not very easy to quantify because it's part of a much larger system, and it all depends on how you account for joint costs of lines, and those lines are shared by long distance trains and so many things. But metrics are there. They are increasingly sort of getting sort of fine tuned and more sophisticated and more usable, and there's tighter control, and there is more user answerability to these things also. So public, of course, the public has got a role to play in this. You should demand better services. There have to be active feedback from users regarding various things. So that is something which I feel is also required from our community, which is that public transport has to meet the public need, and then the public has to get involved in defining these metrics regarding frequency, usage, and route coverage, and all these things. So only then there will be a good provision of services. It will not just happen by chance. So sports is fairly. I won't motivate it too much, but I'll just go to the right side of the slide here. That uh, you know the sports that I'm going to talk about, there is a basic unit of like winning a point, like in tennis, or I assume that everybody here will have played some or other sport of the type that I mentioned. So in table tennis, for example, you win a point by doing certain things, uh, and in each of these games, you earn points, and you accumulate those points in a certain structured way, and then you win the game. But it is you would have observed that it is not just that you play 1000 points and then whoever wins more, I mean, it has to be an odd number, whoever wins more points, they win the game. It is not like that. For example, in tennis, you win a certain number of points, then you win a game, you win a certain number of games, you win a set, you win a certain number of sets, you win a match. So it is a hierarchical structure. So you might have wondered why that is so. And in table tennis, for example, you win certain number of points, you win a set, and you win a certain number of sets, you win the match. So there is no concept of a game in table tennis. Whereas in tennis, it is in a four-tier hierarchy. There's a point, there's a game, there's a set, and there's a match. And in table tennis and badminton, there are three levels of hierarchy. There's a point, there's a set, and there's a match. So in all these games, there is a structure of these things. So what is the reason for this, and what does it the implication? So what are the objectives? One is fairness. I mean, the game has to be designed in a way that the better player should by and large win. Not always, because that is the reason you play the game, that to discover who is the better player. But by and large, if you have worked hard in the skill of the game, and you know how to accumulate points, then you should win the game by and large. uh, there should be some chance for the underdog. Otherwise, there is no fun in the game, right? And then the length of the game, at least in expectation or on average, it should not last forever or something. Yeah. So let's go further. So table tennis. So those I don't know the average age of participants here, but you might remember a time when table tennis games were 21 points. At least when I was growing up, table tennis was 21 points, and you have to win 21 points to win a set. And if you reach 20 all, then you played deuce type of thing. There has to be 2 point difference and so on. So sometimes the game would be 22-20 or 25-23 and so on. And then you won a set, and then it was best of 5. This is what I remember. If people have some other memory, you can tell me, but I hope at least one or two of you will remember when table tennis was like this. Currently, the scheme is it's 11-point game and best of 7. This is what I understand. I don't play table tennis these days, but what I understand is that it's a 11-point set, uh, and then you win. It's a best of 7. So you play more sets, but shorter sets. You have to reach only 11 instead of 21, and play fewer sets. So what is the reason for these things? And if you check it, all these games have had rule changes. Table tennis has had a rule change in the last 25 years. Let's say they have had rule changes of what defines the winner. So earlier, if you remember, badminton, you could win a point only when you had the serve, and to win the serve, you had to win the point. I mean, then you got the serve, and then you could gain a point. So this meant that sometimes the serve would keep on changing, and then you played for a very long time without the score improved, without the score progressing. Now in badminton, you can earn a point even without serving, and that has speeded up the progress of the game. But again, there they made it 21 points instead of 15 points. So in badminton, when I was playing it as a child, or growing up as a teenager even, it was a 15-point game, and you had to win a point only on serve. And I think the same thing is in volleyball also. So the schemes are evolving, and what is the reason for this? Okay. Yeah, go next one. And then the main thing in these things is, so badminton, both of these I have said. Yeah, let's go ahead. So uh, the other interesting thing is, to design a scheme for a game. I'll call it a scheme. This 11 11-point sets and best of 7 versus 21-point sets and best of 5. So these are two different schemes for table tennis, and so on. uh, I Whatever be the scheme, supposing there's one player who's dominant, who's really good, and is much better than the other player, and let's say the probability of winning a given point is something, a serve or no serve or whatever. There are variants in how you model the whole thing. Then it doesn't really make too much of a difference, what the game design is. Whatever be the game design, the better player is going to win most of the time. Okay. So the real analysis is when two players are almost evenly matched, and then what happens. Okay. So let's go a bit further. Next one. So for example, tennis. Those of you, I assume that most people would know the scoring in tennis. You start with 0-0, and then whoever wins a point, it becomes 1-0, which is called 15 love. And then you win another point, it becomes 2-0, which is called 30 love, and so on. And then 40 love instead of 45, 40 love, and then game. So this is, if you win 4 points in a row, you go up the top left arm of this fish, and you go to a score of 4-0. If you lose 4 points in a row, then you go to 0-4. I suppose that's clear, right? But you can do many other things. You can win a point, and then you can lose a point, and then you can win 3 points in a row. Then you will wind up with a score 4-1, which is called, game 15, or from 40-15 you make it game at 15. So you wind up with a score 4-1. So I'm using now 1, 2, 3, 4 to represent the normal scoring which they announce in tennis games as love game, love, and 15 and 30 and 40 and game. So game means 4, and 1 means 15, and 2 means 30, and 3 means 40. Okay, in the normal way that score is announced. The interesting score is, of course, 3-3. That is, both players have won 3 points, and then that is called deuce, because by this time in the game they have shown that they are almost equally matched. And then you don't want to just make it a random, there is a net ball, or just inside the line and so on. So you want to say that, okay, now you two people are almost evenly matched. One of you show that you are better, and you get a difference of 2 points. So that is the deuce scheme in tennis, and the similar thing is there in almost all the other games when the score is tied. Okay, so from 3-3, what happens? You can go to 4-3, and then if you win another point, it becomes 5-3, and then you win. From 4-3, if you lose a point, then it comes back to 3-3, or it actually becomes 4-4, which is similar to 3-3. Now, you can very well imagine that this 3-3 to 4-3 to 3-3 to 3-4 to 3-3 to 4-3 to 3-3 to 4-3 to 3-3. This can happen for a long time. You can return to this due state, this orange thing in the middle on the right. You can return to this state many times, and in theory the game can go on forever, but that rarely happens. I mean, I have not heard of somebody continuously playing tennis for months on end or something. Sooner or later you escape that situation. One or the other wins. Of course, by doing this you only win a game, and then you have to win several games and so on. But let us just analyze this 3-3 just for the next one. So what is the average time that it takes from this due? So this is actually fairly standard applied probability analysis, that this is a Markov chain with certain absorbing states, which are the winning states for the game. And you can very easily do a small analysis. When I teach this in the class, or I show it in the class, students have their own way. Somebody writes a sequence and then sums it up, somebody else does a recursive equation, somebody else does some other intuitive thing, and then you actually work it out. So it actually, the expected number of points on average. So supposing you play several games of this type, from the deuce, I'm talking from the deuce point onwards, the expected length of the game, the expected number of points played is given by 2 over r, where r is 1 minus 2p plus 2p square. And what is p? P is the probability that one of the players, let us say player one wins the point. So then, so this, it has to be symmetric in P, because if player one wins a point or player two wins a point. So it actually is, if you plot this function 2 over r, where r is 1 minus 2p plus 2p square, it turns out to be, it is symmetric in P with at half. So P of half plus something is equal to P of half minus something. It actually achieves a maximum value at P equal to half, which is sort of intuitive, that it will take longer to decide from the due state when the players are equally matched. When the probability of winning is half, then both the players are equally matched. It takes the longest time to this thing. So, and beyond that, I mean, anything away from half, it sort of tails off. For example, if P equal to 1, then one of the players is anyway going to win 2 points in a row, and then that's it. If P is equal to 0, the other player is going to win 2 points in a row, and that's it. You can easily plug in those things, and you will get all those values, and you can work out the average time of a game. So this is one performance measure. You go to the next one. So now the question is that instead of this deuce thing, why don't we just make it a best of 3 starting from deuce, or a best of 5 starting from deuce, or a best of 1 starting from deuce? I told you why we don't do a best of 1, because that's too chancy. Because you've shown that you're almost equally proficient at that point, and just by winning 1 point, you will win or lose the game. That doesn't seem nice. A best of 3, why don't you do a best of 3? Ignore the serve advantage, okay, for the time being. You can actually play with the serve advantage by, changing the dimension of the court slightly, which they do actually, because they've made the, serve area slightly less and so on. So you can play with that. Let us say the game is designed so that serve has not got a significant advantage, just to keep the thing simple. Why don't you do a best of 5, let us say, for dues? So the answer is in the next slide, I think. uh, or Yeah, actually, let's go even one slide further. uh, next one. This one. So uh, on the x-axis I have plotted the chance of winning a point. Okay, so let us take from my point of view. I'm playing the game, and P is the chance of my winning a point. So P is a number between 0 and 1. So this is my skill in the game. If I'm a very bad player, my chance against a particular opponent is 0. If I'm really proficient against the other fellow, my chance is 1. I am somewhere in between. Some probability between 0 and 1 is my proficiency, meaning my chance of winning a point. Okay. So then my question to you is, what is the probability of my winning the game? So I have to play a certain number of points in a structured way, and then I win the game. So that the 45-degree line is a completely fair game. That means the chance of winning the game is equal to the chance of winning the point. Okay. Now let me ask you this question: that supposing from the deuce point onwards, you have to design a game which is completely fair. That means if I have a 0.55 chance of winning the game, of winning the point, then I should have a 0.55 chance of winning the game. Then with a little calculation, you can work out that you have to play a best of 1001. Then, the better player will always win, even if it is 0.51 or 0.501. The better player will always win if you play a best of 1001, okay, or 10,001. But that will take forever. So most games are designed that without taking forever, you want to give the better player a chance of winning, which is fair. Now when I say fair, it should be below the 45-degree line and above, on the left side, and above the 45-degree line on the right side, because on the right side I am the better player and I should have more chance of winning the game, and on the left side I am the weaker player and I should have less chance of winning the game. So I cannot exceed the 45-degree line. That would make it a game of chance. Okay. So the blue vertical, 45-degree line is a completely fair game. The limiting case, which is the red S-shaped, sort of S-shaped curve, is a brutally fair game. That means if I'm even slightly better than the other player, I have 100% chance of winning the game. And if I'm even slightly, you know, less adept than the other player, I've got 100% chance of losing the game. That means 0% chance of. So that is the, 0 up to 0.5 and then 1 beyond 0.5. What happens at 0.5, of course, you can't say, because that they're evenly matched. They'll play forever to decide who is better. But if I'm even slightly above zero point 0.5, I should win the game always. If I'm slightly below zero point 0.5, I should lose the game always. This will be achieved if I play a best of 1001 or a best of 1000, a very large number of points, and take the best of that. You can easily imagine that, because eventually I'm going to, establish my superiority, even if the difference is very slight. Is that okay as a principle? As a just as a mathematical principle, and it you can easily work out it is. See, if I play best of 5, let us say, then what is my chance of winning the game? I have to win 3 out of 5. Now I can win 3-0 or 3-1 or 3-2. So you can work out those probabilities given the probability of winning individual points, and you can plot. It turns out that the chance of winning the game for a best of 3, best of 5, best of 7, etc., is all these S-shaped curves. So the what shall I say? The blue 45-degree line is a best of 1, and the red S-shaped curve is a best of infinity plus 1, or a very large number, odd number, let us say. And S-shaped curves, continuous curves going to that limiting S-shaped curve, are best of k for increasing k. Is this principle okay?
Yes, to me.
Okay.
But yeah.
So the next slide shows some simulations that we have done and some calculations that we have done. It turns out that, so this is for table tennis actually. It turns out that for if you play 5 sets of 21 points, that's a red curve. And if you play they're all these S-shaped curves. Actually, all of these are S-shaped curves. The scheme design of 5 sets of 21 points is the red S-shaped curve. the cyan or whatever that greenish thing is, teal or some, I don't know what those, teal or whatever that, 7 sets of 11 points is the sort of lower curve on the right side, and a higher curve, but they're all pretty much the same. They're not that different. But what is different is the expected length of the game. So the fairness of the game is all these S-shaped curves, uh, below the 45-degree line on the left side and above the 45-degree line on the right side. They are all fair games. There are completely fair game is the horizontal, I mean the 45-degree line. The brutally fair game is the S-shaped curve. Anything in between is, okay, as a game. But the next slide shows that the average number of points played is quite significantly different, and that is the bottom half of this curve. And it turns out that, uh, I, if you see the top part of this curve, it turns out that deuce and best of k, best of five, is almost the same in terms of percentage of winning for the better player, and percentage of losing for the worst player. But the number of points you play on average is significantly less in the deuce scheme. Although it is true that in deuce you can play a very large number of points by chance, but that will happen rarely. You can easily imagine that if I'm a much better player, then deuce will be over in 2 points. Whereas best of five, I still have to win 3 points. I have to play at least three. So it turns out that best of five is approximately equal to deuce, and for p equal to zero point 0.5, it is the same, in fact almost same in terms of the probabilities of winning the game. In fact, it is the same. All of these schemes will be at p equal to zero point 0.5. It will be at zero point 0.5. The chance of winning the game is equal to zero point 0.5, which is the chance of winning the point. That had better be the case. But the length of the game can vary significantly based on the game design. So the upshot of this, since I've run out of time, is that table tennis moving from 21 points best of 5 sets to 11 points best of 7 sets is almost the same in terms of the chance for the underdog and the chance for winning for the more adept player and all those things. And at p equal to zero point 0.5, it is almost the same. However, the average length of the game is significantly decreased. So that is one good thing. So you can play more games and have more fun. So that is the upshot. And many other analysis one can do of different kinds of games. The last point I want to make is the type 2 game, which is like your penalty shootout in football, where you don't earn a point when the other player is shooting. You have to take your turn. So it's not like a type 1 game where in any given point either of them can win. So that has got a slightly different analysis, and we have done something on that as well. So if you can just sort of cycle through the last 2 or 3 slides, it will be nice. Table tennis simulations we have done for these things. So the expected length, the best of seven, uh, is significantly better than the best of five 21 points. Yeah. Then type B games, as I said, where like a penalty shootout or like baseball or something, where when you play an inning, only you can score run. The other team cannot score run. They can prevent you from scoring, but you can. Yeah, and then next one. So this is for the effect of hierarchy. As I said, in tennis, when you make a 3-4 tier hierarchy, you can see the impact here. Yeah, type B games, as I said. Um, yeah, there are some propositions which most of them are fairly common sense actually, and verified through some combination of simple mathematics and some simulations. Next one. Yeah, baseball, which is of my interest. Actually, it's a traditional game where the rule changes are quite rare, but they changed the extra innings rules about 4 years ago. And the impact has been that extra innings, that means where teams are tied at the end of regulation time, regulation innings rather, the number of extra innings played has come down, which they wanted, to make games close to 2.5 hours rather than going on for 4 hours or something. Yeah. Uh, so we can analyze type 2 games also, penalty kicks and so on. Uh, and it turns out that you had these S-shaped curves in the type 1 game, and here you have these nice saddle point games. So here also some nice curves are there, and I won't go into this. Yeah, I think the next one is the last slide, I think. Yeah, these are all, like for example, in December in Udaipur, IIM Udaipur, there is a Match Sports Asia conference where people are gathering to discuss various applications in sports. Unfortunately, I'm not going there, but people are, of course, not. This is not the only thing. In fact, I don't know if anybody is going to talk about these kind of things, but about sports scheduling and team selection and so many other things. And on the right is CASPT, that is computer aided a conference on advanced systems in public transport and transit in 2025 in Japan. So these are all, public transport sports. These are all quite well established in their niche, and a lot of interesting things are happening. Both. This is all that I wanted to say. Thanks very much.
Thanks, thanks a lot, Professor Rangaraj. That was really fascinating, and I mean, covering two very interesting topics, according to me at least: game theory and operation research. Uh,
Not so much game theory actually as game design. With game theory has
okay.
got this, strategizing and all that. That's a game theory is a slightly different subfield. I'm not the
Oh,
best
okay,
person to
okay,
talk
okay.
about game
I
theory,
see.
but game design and organization of games, yes. Sports, I
Okay,
would say
okay.
yes.
So the
Game
game
theory,
theory doesn't intersect with this in game design.
not in this because game theory actually talks about the strategies employed by multiple agents. So this is more about, you can say mechanism design or game design or something like that. Maybe it has got something to do with game theory, but game theory, the usual, Nash equilibrium or whatever one talks of, that beautiful mind and all those things, that is a different flavor altogether.
Okay. Uh, so participants can ask questions by unmuting themselves, or if you have trouble with your microphone, you can always type your question in the chat.
Yeah, I would like to ask one question.
Go ahead.
Sure. This is Vipul Kakkar from Department of Mathematics, Central University of Rajasthan.
Yes.
So, actually, I work in algebra group theory,
Uh-huh.
but I have seen some paper of integer programming
Uh-huh.
in integer linear programming in modulo arithmetic.
Uh-huh.
So optimization of linear programming, integer programming in modulo arithmetic.
Yeah.
So do these paper have some application in real world, or
So
they are?
no, no. As I said, this periodic event scheduling problem, where I said that modulo arithmetic is used. So where the arithmetic is not on the real line, but on a circle or a period with some period t, this modulo arithmetic is actually the device which is used to model all those constraints in a linear way, subject to certain integer variables in the modulo arithmetic. So actually, they are the periodic event scheduling problem which I spoke of is exactly one of the quite actually turned out to be quite pervasive application. That has got a lot of interesting applications in scheduling of various kinds. So periodic scheduling, modular arithmetic is very much tied up with periodic scheduling.
And I have seen some paper that integer programming related to group theory also. But
So
I
that I am not familiar with that subgroup, that sub area of work, but I am aware of what you are mentioning, but I haven't myself seen those
okay.
papers. But I would imagine so. I would, yeah.
The thing with the metro and public transportation, I think everybody would have experienced. But recently, or relatively recently, it was interesting that I was somewhat. I was playing a game called Mini Metro. I don't know whether you know about that.
No, no, I don't actually. I
It's
be
a
happy
very
to know.
interesting game. It's a very simplified somewhat abstracted game
Uh-huh.
where you start with a map and
Uh-huh.
then you're given 2 points to begin with, and
Uh-huh.
you just draw a metro line, and you can
Uh-huh.
add more carriages to it depending on how many people turn up at each end. And then over time, you keep on increasing depending on your point. You keep on increasing, adding more points. The more points or demand show ups in different parts of the city as
Uh-huh.
points, you connect it and you decide. Essentially through intuition you try to decide step by step very strategically.
This is
uh,
exactly the sort of thing that I would love to play around with. I think I've just been so caught up in the real world of Delhi Metro and Bangalore Metro, but I've forgotten to look at abstractions and the more fun ways of approaching this. So I really thank you for this
right,
pointer. If I'm
I'll
not able
send
to
you the
find it,
link.
I'm going to ask you, for
No,
that.
I'll send you that link
Sure,
because I
sure,
love
sure.
playing the game. It's also, I think a lot of research going goes into optimizing such games too, so that any
Oh,
random player with no knowledge of scheduling and all this operation research can still slowly understand, slowly sort of make the connections and build up and improve strategies
absolutely,
and things like that.
absolutely. I mean, making gamification of these tools for learning purposes and for modeling, etc. That is in fact a big area in our community also. How to expose people to these modeling paradigms and tools, and this would exactly be what we would be looking for in this area. I mean, so I look forward to mini metro as soon as I get off this call.
Now I also realize that I've been thinking about, games and sciences too, which is very hard to do. Which it's
Uh-huh.
very hard to create a game which is very interesting to play as well as it teaches you science and stuff.
Uh-huh.
But I feel that operation research is the sweet spot where there's a lot of strategy games. I especially like many of these strategy or optimizing games where
Uh-huh.
it would be abstracted out some industry or creating some research. It's sometimes not even proper names and all that. It's
Right.
just that somehow you're able to abstract all those ideas and try to, optimize the output, optimize your currency or whatever.
Absolutely.
So there are many
Board
games,
games.
many such
Actually,
games like that.
board games are a great way of thinking about OR because that is roughly the mental model that we all have. Actually,
Right,
it's
right.
an abstraction. Yeah. So many interesting board games exactly capture the flavor of what you're saying.
Right, right. But nowadays, because of this, computer games, there it has exploded a lot. There are probably thousands of such
I
simulations
agree,
and
except
strategy.
that some of the collaborative aspects and some of the dynamic human this thing that is still captured through physical board games.
Uh-huh.
I find that students
Sure,
still
sure.
enjoy
Yeah.
playing board games whenever they have the leisure to spend an hour. They actually enjoy board games whenever
Right,
it
right.
is possible. But I agree with you. Computer games
Yeah.
are probably more development in those in the last
Mm.
few years. Sure. So I
Hi.
must say that public transport I have been working on for a very long time. So I have given this, but this is the very first time I'm actually talking about sports. I tried it in a course, half a course here, but to a
Mm.
larger audience, I'm speaking about this sports business thing for the very first time. So I must thank you for the opportunity
Yeah,
to
sure,
do
sure.
that. Although it was a bit hurried, but still, I think I
Right,
fetched.
right. No, it was, I mean, of course, understanding it in somewhat more detail, the mathematics of it, of course, will take time.
Ah,
But it was nice to see aspect of it many of us don't even think about or rarely
right.
think about that, how strategically you can design these
Design.
games and particular aspects of these games
Sure.
to ensure it's a fair game and things like that.
Sure.
I think there's a last question in the chat.
Sachin Raju.
Yes.
Making a college level timetable. Let me just open the chat.
Oh, I can read it too.
Oh, yeah, sure. Yes, yes. In fact, my colleagues, they have been the institute timetable coordinators for many years. Once our department acquired some visibility, our administrative deans and so on, they figured out that these fellows are the right ones to, because you have slots, you have instructors. Two instructors cannot teach two different courses in the same time slot. Two students cannot register for multiple electives in the same time slot. They have got compulsory courses. There are classroom constraints. There are projection constraints in the old days. There are classroom size constraints. There is minimizing the walking time of students. So classroom timetabling is a very serious integer programming problem, which there would be conferences on that very topic.
Hmm.
And at least two of my colleagues have had significant experience in actually trying to do it for our own institute. And in fact, they have helped some other institutes as well.
That's
So this is
great.
very correct.
Thanks a lot, Professor Rangaraj, for taking the time. It was really a fun evening.
My pleasure.